Hello, this is Ken Stuzen. I'm a partner at Brown Advisory. Welcome to the Now Podcast. Now stands for navigating our world. Through these discussions, we try to understand the world better, to navigate some of the most pressing questions that are shaping our lives, our culture, and our investment challenges. Two seismic forces that are shaping our world, deglobalization and digitization, are colliding over a single inflection point: semiconductor chips. Chips are the building blocks of the global economy, an irreplaceable component of tens of trillions of dollars of annual economic activity. Geopolitically, the stakes could not be higher. In this conversation, recorded at the Now conference in June 2024, my colleague Ben Bayat speaks to Chris Miller about the battle for this crucial technology. As an investor in semiconductor companies, I found their conversation illuminating, and I hope you do as well. Ben and Chris discuss the true marvel that is semiconductor manufacturing, the global supply chain and its risks, the CHIPS Act, the state of the global semiconductor industry, and national security implications, and frankly, a lot more. Now, over to Ben.
Wonderful. Thank you, everybody. So I'm Ben Bayat. I'm a managing partner of NextGen Venture Partners, which is a venture capital firm within the private equity strategy at Brown Advisory. We're really thrilled to have the opportunity to moderate this panel with Chris today, because I actually spent the first half of my career in the semiconductor industry. But more importantly, this is the book for this moment in time. Semiconductors have created the foundation of our modern world. And the US and China, as we just heard, are kind of laying the groundwork and setting the weather for all of us in that geopolitical situation. So the fight over semiconductor design and manufacturing capability is really at the heart of that. So I don't think we're overstating it to suggest that this topic and your book as a guide to it will really dictate the near term future for us globally. So really excited again to have Chris Miller with us. Chris is the author of Chip War, The Fight for the World's Most Critical Technology, which has won several awards, including the Financial Times Business Book of the Year. And in his day job, Chris is a professor of international history at the Fletcher School at Tufts, where his research focuses on technology, economics, geopolitics, and Russia. Chris, thanks for being here with us.
Thank you for having me.
Yeah. So as I mentioned, I started my career and I spent about 15 years at IBM Microelectronics. And as I was reading your book, it was like a memoir of my time there and why myself and several of my colleagues former colleagues that are here in the crowd took an off-ramp from semiconductors. Because you do and I was so grateful because you do such a nice job of describing and articulating the challenges that really I was unable to do it at that time. So I lived a lot of that experience. And I would love to set the stage from your perspective and what you've really made so accessible in that book of let's give semiconductors their moment for a second here and set the stage. Talk about the importance and really how you view the evolution of this technology relative to any other in human history.
Well, I think to start, we've just over the last couple of years come to realize the extent to which our entire lives, our entire world are structured by thousands and thousands of semiconductors. In the microphone attached to my shirt, in the phone in your pocket with actually dozens of semiconductor devices, in your car, or if it's a new car, it'll be 1,000 semiconductors, in the data centers that store and process all of our data, and the telecoms infrastructure that makes it possible to like something on Instagram or to send a text message. All of this is reliant on chips. And it's become possible to put chips in basically everything because the cost of computing power has collapsed over the past 75 years by roughly a billionfold. Nothing else comes remotely close to that declining cost or the improvements in performance, which is the flip side of that equation. And so that basic dynamic explains why there are chips in everything and why we rely increasingly on chips and the AI that they make possible for a larger and larger share of our technological advances and the productivity improvements that the entire economy depends on.
Right. So we'll get into newer evolutions of use cases for semiconductors in a moment. But let's talk about that evolution in Moore's law. Maybe start to give us a sense of scale on this. So a semiconductor, a microchip, a transistor, a gate, a lot of these terms that will help orient us all to the conversation. Can you give us a sense of scale, both in terms of what is Moore's law, how do we think about 3 nanometers? Let's start with some of that.
So the first chips that were commercially produced by companies like Fairchild Semiconductor, which was founded just down the road in Silicon Valley, had a handful of transistors on them, little switches that would turn circuits on and off. And roughly speaking, the number of transistors is correlated with the amount of computing power a chip has. Today, if you go to the Apple Store and buy a new iPhone, just the primary processor will have 10 or 20 billion transistors on it. So there's your billion-fold increase in computing power right there. And that's been possible because we managed to shrink transistors smaller and smaller and smaller in a way that was predicted by Gordon Moore, one of the co-founders of Intel, who just passed away last year. And what that means is that today there are 10 or 20 billion devices smashed into a piece of silicon the size of your fingernail inside of your smartphone. And to do that, you need to have each one of them be very, very small. They're roughly speaking half the size of a coronavirus. And to manufacture devices at that scale requires the most complex and precise manufacturing that humans have literally ever undertaken. And so Moore's law and the technological improvements that make software possible, make AI possible, all of that's been underwritten by manufacturing improvements, the ability to manufacture at nanometer scale. That's a billionths of a meter, which today we rely on for basically everything and take almost completely for granted.
So something akin to nearly landing on the moon in an economical manner every single day, sitting on our phone, enabling us to play Angry Birds, that we've become almost taken for granted. But the magic of being able to have made it economic provides the ability to have the advantage of creating scale and consumer utilization to that. So let's use an example around when you talk about the tooling necessary to do this. Let's talk about ASML for a moment. And photolithography, which is critical to the manufacturing of semiconductors, there's a single source for that. And can you talk about the challenge and what is the complexity of their supply chain? What is the complexity of the engineering feat that they are able to do billions and billions of times per microchip? And how did they get there?
So to produce a chip with billions of virus-sized components on it, you undertake a process called photolithography, which until recently, almost no one who wasn't employed by ASML was a word that they could pronounce. And now there are even political leaders who can say that word. And photolithography is essentially a process of printing with rays of light. That's sort of a really simple way to describe it. But the rays of light that we print with today must be fine enough to make it possible to produce nanometer-sized devices. And so the light we can see is actually several hundred nanometers in wavelength. That's actually too broad of a brush with which to paint the tiny transistors that our semiconductors require. And so today there's a company called ASML based in the Netherlands which produces a machine that can produce light at a wavelength of 13.5 nanometers, which is fine enough of a tool to produce the transistors on your chips. And to produce light like this requires the most complex and expensive machines that humans have ever made. A new ASML tool will cost $150 million a piece, require hundreds of thousands of components, including the flattest mirrors humans have ever made, the most powerful laser ever deployed in a commercial device, and an explosion happening as a ball of tin, 30 microns wide, is pulverized by this laser with 2 big blasts, explodes into a plasma measuring 40 times hotter than the surface of the sun, which emits light at just the right wavelength, which is then collected by these mirrors and shined onto the piece of silicon that becomes the chip inside of your phone or inside of your dishwasher. And to make this happen, it requires a supply chain that stretches across the world. ASML assembles these machines, but it does so using components from California and from Germany and from Japan. Hundreds, thousands of suppliers that ASML has cultivated over the 3 decades in which they've been trying to develop these types of tools. And that's why they're the only producer in the world, 100% market share of the tools without which cutting-edge chips are basically not possible.
And so let's, in that supply chain for a moment, so from a tooling standpoint, equipment, kind of 5 leading companies, 3 in the United States, 1 in Japan, 1 in the Netherlands. That alliance, apropos to the prior conversation, critical for security around these supply chains for semiconductors, as well as our economy's availability to access them. We have a phrase, an adage in semiconductors that hardware and software leapfrog each other. And so as you move down Moore's law and there's more compute, software consumes that with more angry birds. But how did we get to the point where we took for granted what you just described as a absolutely fascinating and feat of engineering to be able to print things that are atoms thick? How did we get to the point where we were taking that for granted and today have come back around now with the CHIPS Act, with more investment coming into the space? What's the temperature today? Is this across political, socioeconomic? How are we aware of it? What's the political temperature around it?
Well, I think that we've come to take the industry for granted because it's worked so well. It has very rarely broken down, which makes it possible not just for typical people, but also for tech companies to generally ignore where their computing powers come from. Most software companies, until very recently, didn't have to think about compute. They just got more compute every year. Intel made them better chips every year. They didn't have to think about it. And so your software could be pretty inefficient because you knew your compute budget would double every 2 years. We've spent the last 2 decades praising our software engineers, but imagine that. The resources that they can consume are doubling every 2 years. There's no incentive for efficiency. And to a large degree, that basic dynamic continues. We still get a more or less doubling of compute every 2 years with some cost questions, some energy questions on the margin. But 2 things changed over the last 5 years. The first is that during the pandemic, there were some shortages in supply chains that caused disruptions, not to smartphones or to PCs or things you might think of as relying on technology, but to the automobile industry, which helped sensitize everyone outside of Silicon Valley, the extent to which the rest of the economy relies on chips too. And so you had car CEOs going to Washington asking for more chips, and political leaders in Washington saying, we have no idea what you're talking about. We know nothing about this issue. We haven't thought about it in about 70 years. That's the first thing. The second thing is that as the industry has grown, so too has the demand for concentration, because there are huge economies of scale in chip manufacturing. And so there's one company today which produces around 90% of the most advanced processor chips. And that company happens not to be located in Switzerland or in New Zealand, but in Taiwan. And it's becoming more and more important over the past decade, just as the security dynamics that the previous panel was discussing have become, I think, more acute. And so there's been a realization in the United States, in Japan, in Europe, that their entire economies are dependent on one company on one small island, which Beijing happens to consider a renegade province. That's the second aspect for why chips are suddenly front and center in a way they haven't been for decades.
So I was really struck that in your book, you do a really nice job of being able to identify the sources of the catalysts for innovation in semiconductors. And to overly simplify, maybe break it down to that it has bounced in the early days of semiconductors, it bounced back and forth between DC, NASA, DoD, and here in San Francisco with startups and venture capital. And so as any good VC, I will inflate the role of venture capital and our role there in just a moment, but let's flip first to the political side of this. And as I understand it today, the US government's strategy largely includes 2 approaches, which is to promote the CHIPS Act and protect through export controls. And so somewhere about $40 billion in incentives, $330 billion in investment yet to come over the next 10 years. TSMC, a fab in Arizona, another fab in Ohio with Intel. The outcome of which is, well, we have all sorts of hopes for economic outcome here. The base expectation or outcome that we're driving after is to reduce U.S. reliance on foreign supply chains. How is it going? How do we judge success? And what's yet to be really tested here?
So I think on the positive side of the ledger, there is undeniably an absolutely colossal rate of increase in investment in chip making facilities. You already see it in the data. It's something like a 10xing of the trend of investment relative to the prior decade. So a ton of huge facilities being built that absolutely would not have been built in the absence of the CHIPS Act. So that's the good news. And there really is going to be a significant increase in chip production and therefore a reduction in reliance on Taiwan and China produced chips as a result of that. On the negative side, there are two questions. The first is, well, we're going to slightly reduce our reliance, but not completely. Best estimates are that the US will produce around 15% of the world's chips within a decade, but we consume 25% of the world's chips. And a lot of the hardest chips to produce will probably still be produced in Taiwan for at least the next half decade, harder to predict beyond that. The second question is, can we do it profitably? We know factories are being built. Shovels are on the ground right now, tools are being purchased, they're being installed, but it's a different question as to whether those facilities will be economically viable or whether they'll be significantly more costly than producing in Taiwan or in Korea or in China. Best estimates are that there's a 20, 30, maybe even 40% cost differential between producing in the US and producing in Taiwan. Government's going to subsidize 10, 15, 20% of that differential. And so there's a real challenge that I think all the companies investing in the US face is to how do they close that cost gap, A, or B, can they find a way to make someone else pay for it? Their customers, for example, who obviously don't want to have to pay for any sort of cost differential. And so that's the second big question hanging over all this investment is, will it make economic sense for the investors in these projects?
So let's double click into that part of it, which the role that I had in semiconductors was what's called a yield characterization engineer, which is really focused on yield as a representation of how many out of 100, let's say, how many of the chips that you produced actually worked. Can you give us a sense of manufacturing in semiconductors by comparison to any other high capital intensive manufacturing process? How unique is that? And the economy of scale necessary to compete, even marginally so, with TSMC, what kind of evolution does that typically look like?
Every new cutting-edge chip-making facility that is built is the most expensive factory in human history. So that's the scale on which we're talking about. The investment that Samsung is currently making in Texas, building a big new chip fab, is the second largest foreign direct investment in American history. Second only behind the investment TSMC is making in Arizona, which is the largest foreign direct investment in US history. So the scale is mind-boggling. If you visit these sites, they have, in the TSMC fab in Arizona, they got one of the largest construction cranes in the world moving vast steel beams around. And one of the ironies of chip making, which I at first didn't, it took a long time for me to understand this, was that to make things very, very small, you need factories that are extraordinarily large and capital investment budgets that are even larger. And so the scale dynamics, I think, will persist as far as the eye can see. And that means that if you're trying to catch up from a position of being subscale, which is where the US is, you've got a interim period between where you are now and where you'd like to be at the end of scaling, where you're going to be more costly because you don't have the infrastructure in place, you don't have all the chemical suppliers, you don't have the rest of the ecosystem built out. And so a key question for the US is how rapidly can you get that ecosystem built to replicate the type of scale that they've got in Taiwan or Korea? And it's not an easy thing to do at all.
Moving over to the protect side, which is on export controls, can you give us a framework here of what does that include and that foundry knowledge that might be an aspect of that? How successful have these measures been thus far?
I think the theory of the case behind the US export controls are more or less the same theory of the case behind a lot of the big companies that are developing frontier AI models, which is interesting. The theory is the following. First, advances in AI depend on scale. Bigger system you train, the better it is. If you want to train a bigger system, you need more and more high-powered chips. Therefore, access to the GPUs, the chips produced by companies like NVIDIA, are a critical component into building complex AI systems. In the past 18 months, that has looked like a pretty good bet. In fact, all of the world's biggest tech companies have been scrambling to get access to GPUs. And so the US government's export controls, which were released 3 weeks before ChatGPT, in some ways look rather prescient. The second part of the theory of the case the US has is that it can stop China from developing these chips domestically. Right now, that bet is more or less working. Almost all of the world's GPUs are produced by TSMC in Taiwan, nearly 100%. That's today. But in 2 years, 4 years, 6 years, China's pouring tens of billions of dollars a year into building out its own chip-making capabilities. It's got very bright engineers, many of whom have worked in the international chip industry at places like TSMC. It's got the entire Chinese market, the world's second largest economy, which is going to buy all of the chips that China produces. And so China is going to pour more resources than anyone in history in trying to build the supply chain necessary to produce cutting-edge chips. And it's going to be really hard because in addition to not selling China the chips, we're also preventing companies like ASML from transferring to China the tools that are used to make these chips. And so if you're China, you've either got to find a technological pathway that doesn't require these tools, to which I say good luck because the rest of the industry has been looking for that pathway too for the past 3 decades and hasn't found it. Or you've got to replicate what the rest of the world has spent the last several decades building. And replication is not impossible. The question is how quickly can you do it?
So on the replication piece, what are the analogies that might hold from the 60s, 70s, and the Russia-US example of this? And what analogies might not be relevant here?
Well, I think that during the Cold War, the Soviets were obviously trying to replicate US technology too. It was regularly the case during the Cold War that the US would capture a piece of Soviet military equipment, take it apart, and find Texas Instruments chips inside. They would literally either seize or directly copy these chips in the Soviet Union. It was so bad, actually, that the Soviet Union, despite the country being on the metric system, had chip-making equipment that used inches because they were so focused on copying American technology. And China's, to some extent, doing the same, with a key difference. And the difference is that for the past several decades, China's been deeply integrated with the rest of the world economy. And so if you look at the CEOs of China's leading chip companies, most of them have served years, if not decades, in Taiwanese or American or Singaporean firms. And so they've got a wealth of expertise that the Soviets never had, an integration with the world market. The US is trying to cut that off right now, but it's cutting that off after several decades in which China's been building up this know-how, which has put China within striking distance, I think, of catching up. It's going to be hard, far from guaranteed, but it's not a 0% chance that they succeed in it.
Yeah, so let's talk about what striking distance means. So to have a vertical stack or an indigenous ecosystem approach that is the measures of these export controls, where are they on the curve of what does advanced capability mean for that indigenous ecosystem in China?
So if you look at chip design to start, the process of designing chips, laying out the transistors where they all go, China's got very strong capabilities there. We've seen it in high silicon, Huawei's chip design arm. And so I think we should not underestimate them at all when it comes to chip design. When it comes to manufacturing, the actual fabrication process, the leading Chinese firm, SMIC, is about 5 years behind TSMC in terms of its ability to use tools from companies like ASML to produce cutting-edge chips. So 5 years is not that far behind. 2.5 Moore's laws behind, ballpark. The problem for SMIC is that they've been 5 years behind for the last 15 years. Every year they advance, but every year TSMC advances. And so the gap remains roughly the same. The biggest problem China faces is when you get deeper into the technology stack. The tooling. Today, almost every chip-making facility in China is almost completely reliant on tools imported from Japan, from the Netherlands, and from the US. That's a huge vulnerability. And China's been trying to build up domestic capabilities, but it's just extraordinarily hard. It's extraordinarily hard to do from scratch. The second place is on chip-making chemicals, materials. If you want to manufacture at basically nanometer scale, misplacing a couple atoms can cause defects in your chip. And so your chemicals materials have to be 99.999999% pure. That's not an exaggeration. That's actually an underestimate for certain of the chemicals that's necessary. And today, China imports many of the chemicals that it needs, including some of the most difficult to produce. And so those are the two core challenges that China faces. Now, they know that. They're trying to replicate. They're trying to build up their own domestic industry, but I think it's going to take a fair amount of time.
So that statecraft that has created these alliances that the United States has, I was struck in the book by, after World War II, that it was technology and semiconductors in large part that the United States used to bind Japan and other East Asian countries. What's the strength of those alliances today? And per one of the other questions, what might a presidential change, regime change in the United States mean for those alliances?
Well, I think the interlinkages that bind the United States, Taiwan, Korea, Japan, and Europe are extraordinarily strong. And they're partly about politics, but they're also partly about technological necessity. Because here's the reality. Our entire technology sector relies on ASML, a Dutch company. And it relies on a bunch of Japanese producers of photoresist chemicals without which chip making is basically impossible. And it relies on TSMC to manufacture all of the chips. So we're reliant on these countries. Thankfully, we agree with them on a whole lot of issues, so it's not that worrisome. And they're reliant on us. ASML produces lithography tools, but they do so with software designed in California and with parts of every tool manufactured in Connecticut. So it's a Dutch company, but it can't function without the United States. And so there are these interlocking interdependencies that link up the Western world. And the challenge for China is that China's on the outside of all of those key interdependencies. Partly, the interdependencies have been made easy to tolerate because they're more or less with friendly countries. No one's worried about getting cut off from Japanese chemicals or the Netherlands preventing the shipment of lithography tools to the United States. But partly it's necessity. These countries have to work with us because we're their largest market, because US tech firms are their largest customers, and because when it comes to the software layer, we're absolutely dominant. So if you look at why the Netherlands imposes export controls on the sale of lithography tools to China, well, partly because if you talk to Dutch security officials in the defense ministry and the intelligence agencies, they're actually pretty worried about China. There have been Dutch warships that have transited the South China Sea to object to Chinese territorial claims there. But it's also because ASML is fundamentally dependent on access to US technology in the US market. And even if they didn't want to, they don't have that much choice.
So it feels somewhat comfortable that we have reasonable political alliances. We actually have alliances relative to the laws of nature that we are, as engineers in this category, are really just trying to figure out how to do this. And so the supply chain has a supply chain, and that ASML, in order to create their tools, has an entire supply chain and dependency on those mirrors and et cetera. That is just how we are figuring out how to print at this level. So let's talk about Taiwan. And over the weekend, as I understand, and saw in a quote, that the US Defense Secretary Lloyd Austin and his Chinese counterpart, to me as a layman, could not have been more far apart on the topic of Taiwan. And the quote that I had was, anyone who dares separate Taiwan from China will only end in self-destruction. So TSMC, Taiwan, 90% of the world's semiconductors, everything requires semiconductors. How do we bridge that gap?
So I think if you look at what governments have been doing across the West, United States, in Japan, in Europe, Korea, there's been a recognition in the last 5 years that they're too dependent on Taiwan. Not because they don't like the Taiwanese, but because if something goes wrong in Taiwan, the cost to the world economy will be measured in the trillions of dollars. And that's not an overestimate. In the pandemic, shortages of auto chips alone, very cheap chips that make your windshield wipers go back and forth and move your window up and down. Auto chips alone caused $500 billion worth of fewer cars to be sold worldwide. That's just cars. If TSMC were to go offline, there would be no smartphones for the next year. PC production would collapse. It'd be almost impossible to build a cell phone tower. They all require chips from Taiwan. So trillions of dollars is the price point. And given the immense cost of losing access to TSMC, governments, including the US government, have said the risk is non-zero. And whether you think the risk is 5% or 10% or 20%, multiply that by $1 trillion price tag, and you ought to be willing to buy a pretty expensive insurance policy. And that fundamentally is the logic behind the CHIPS Act in the US. We're buying an insurance policy in case something goes catastrophically wrong. The nuance is that China is also doing the same thing. And if you ask yourself who's de-risking faster from Taiwan, us or China, the answer is blindingly obvious. It's China. Every projection of chip-making capacity over the next 10 years shows that China will be more or less independent in the types of chips that are needed for dishwashers and cars and coffee makers and everything but high-end AI use cases. China's going to have all the capacity it needs to produce domestically. With our tools, we've already shipped them most of the tools they need. Chinese factories will be able to produce the chips that its manufacturing base requires, excluding the most high-end applications. And so we're heading, I think, towards a much more dangerous dynamic where we're still pretty dependent on Taiwan. less so, but still pretty dependent. And China is dramatically less dependent than it is today. And to me, that is a very dangerous dynamic that we're just beginning to think through.
And maybe one more there, and we can flip over to the business side of things. But as we talked about before, with the influence of the State or Defense Department, we can look at things like guided missiles, and that feels fairly obvious as to how semiconductors might play in that conventional form of warfare that we're even seeing. You maybe can comment on, even in the war in Ukraine, Russia versus the material that Ukraine is benefiting from the U.S. side of the technology. But the next frontier is really around AI and ML, machine learning, artificial intelligence and machine learning. And so those manifest in a different way. And so data as the new oil, and data as information, and information as truth or misinformation. What are the next forms that this type of defense, national security interest might take?
And I think if you talk to folks in the military, they're already using AI-enabled systems on a regular basis. It's already the case that when satellites take photos, there are computer vision algorithms helping sort out what's a truck and what's a tank. That's already happening. There's already a fair amount of autonomy embedded in drones, for example, how they fly, when they take off and land, and that type of autonomy is only going to continue developing. I think next to this sort of the hard military dynamics of how do you deploy AI, there's also a question of who do you want to own the AI infrastructure? And that's the second aspect of why governments are fixated on this question. Right now, if you go into any data center in the world, and data centers are where AI happens, they're full of US chips. You basically can't run a data center without US chips inside of them. In the US, in Europe, in Japan, in China too. Data centers are full of US made chips. And that gives the United States a whole lot of leverage in addition to the obvious business and economic dynamics behind it. And the US wants to make sure that as we enter a new wave of technology where AI is at the center, that the US has a privileged position in the AI stack, whatever that looks like. And the infrastructure, the hardware, the data centers, the chips is going to be absolutely critical there. And the US doesn't want Chinese firms to be playing a major role. It wants US firms in a central position. And the good news, I think, over the last couple of years is that contrary to most people's expectations, except for Jensen's, the US is playing that role to a really spectacular degree in a way that most people in this room would not have guessed 3 years ago.
So maybe on the private capital side of things. So Silicon Valley, not often referred to it anymore. SF Bay Area, have rebranded ourselves away from Silicon. And only recently has there been more investment occurring in the space. As I mentioned, 15 years in the semiconductor industry, moved into the venture capital space. I did not find a lot of use for that network or knowledge, domain expertise. In the last 2-3 years, we've been investing more in the category. And some of the challenge that we experience is that venture capital requires a stair step of capital being raised and demonstration points with either the evolution of a technology or customer interest, some sort of traction point that allows them to raise more capital. And with the capital intensity that's required here, and the opportunity that we've seen over the last 10 to 15 years in which there's easier places to make money in software, where do you see the opportunity in the Bay Area with venture capital and startups? What are the white space that some of the startup founders in the audience might be looking at?
I think the obvious answer to the question is AI, which is where you've had extraordinary value creation the past 18, 24 months. And where there's huge amounts of investment going into, and a lot of that is going directly into silicon. If you ask, what is it that Amazon and Microsoft and Meta are spending their CapEx budgets on? They're spending $10 billion a quarter building data centers, and data centers is just a big warehouse full of silicon. So there's a whole lot more investment in buying high-end data center chips than most people would have thought remotely plausible just a couple of years ago. And so one of the key questions is, well, what does this environment look like in 5 years' time? Right now, it's all about the data center. Everyone is training big models. But there are really interesting questions as to where we're going to be doing most of the AI processing in 5 or 10 years. Is it going to be in data centers? Or is it going to be on device? And the answer is probably a mix of both for different use cases. But that opens a lot of interesting questions as to, well, if it's on device, who's going to be producing that silicon? What are the types of designs that are going to be competitive there? Will it be NVIDIA-centric or will it not be NVIDIA-centric? And that's, I think, the primary area of focus for a lot of startups that are trying to win a piece of this very rapidly growing pie.
So maybe in that same vein, a lot of the conversation tends to be about compute, which is the capacity and capability of these semiconductor chips to analyze data, to simplify it. But many estimates would suggest that the AI compute workloads are likely to have such a significant power or energy consumption that it will make up more than US GDP in several years. So that's a pretty big wall we're coming up against. So can you talk for a moment about how you see the landscape shifting from compute and to power?
So I think on the one hand, when I hear people say that we're going to be using US GDP's worth of energy for AI, I think back to articles you can find from 1998 about how emails will soon be consuming 25% of US energy production. And indeed, there were a bunch of articles written on that exact theme. And in reality, data centers, until the past 2 years, actually didn't really increase their power consumption much at all, even as we built bigger and bigger data centers. Now, I think that is changing in a significant way. And the key challenge is the following. We've been producing chips with, roughly speaking, a doubling of computing power still continuing when it comes to AI processors. But the power efficiency only doubles every 3 years. So you double compute capability every 2 years, you double power efficiency every 3 years, which means you've got a vast gap opening up between your compute capabilities and the amount of power you end up consuming. And that's the core dynamic that we're dealing with right now. And until recently, there hasn't been a lot of focus in solving that problem. And that's changing dramatically. Because right now, there are a bunch of places in the world where you can't build a new data center because there's no power. In Northern Virginia, the data center capital of the world, it's very power constrained. Singapore just recently lifted a moratorium on building any new data centers because they didn't have any additional power in Singapore. There's a bunch of countries in Europe, like Ireland, which have banned new data center construction because there's no additional power in Ireland. And this is one of the countries that is a key data center node in Europe. And so if you're a big cloud computing company, suddenly this is front and center in your thinking about how do you build the compute capacity that your AI plans require. And it's a question both of just raw power, it's also a question of your green energy goals. And I think it's been interesting to watch the past couple of weeks, some really interesting announcements from tech firms in the energy space. I'll just give you 2 examples. One, Amazon just announced last month they're buying a data center campus located right next to a nuclear power plant in Pennsylvania. That's one. 2, Microsoft announced a over $10 billion power purchasing deal with a private equity firm to build them solar power plants across the US. I wouldn't have guessed 10 years ago that tech firms are going to be big energy investors, but actually it's playing out that you've got to be an energy investor if you want to build AI scale data centers.
So this topic is directly in the center of an interesting Venn diagram of geopolitical uncertainty currently, environmental uncertainty, power playing a significant part of that, and a new technology inflection point with how AI will manifest itself in our daily lives. So that's a lot to try to comprehend. How do you talk to your students about living in this world with a multivariate equation that we're all trying to solve?
Well, I was trained as a historian, and I think actually history is the best lens for understanding technology as it interacts with the rest of society, because it forces you to identify trend lines and then stress test when you have inflection points. I started digging into the chip industry, wanting to understand how was it that computing developed in its earliest days. And I quickly learned that actually some of the key trends that started in the Bay Area in the late 50s more or less persist all the way up to the present. A desire for cheaper compute, a desire for more compute, a need for ever more complex supply chains to produce the nanometer scale manufacturing that's necessary. All of these are long-standing historical trends that continue. They change in their context, but the history I think is really critical. And so when I look at AI, nobody knows projecting forward what AI is going to produce in 5 years or in 10 years, what business models, what capabilities, what regulatory backlash. But you can look at prior technological shifts and at least get a sense of what one might expect. It seems plausible looking at the software era of the 90s and 2000s and the antitrust concerns that brought to bear, that if we still have a small number of big firms that have dominant positions in AI and in providing AI chips, that one might expect antitrust concerns to reemerge, for example. That's just one example of many that you could think of, which I think is not rocket science to think up. It's rather just a question of looking at what's happened in the past. We've had technological revolutions like this and trying to develop a sense of pattern recognition between what happened then and what is happening right now.
Wonderful. Well, Chris, thank you again. Thank you for researching this book. Thank you for writing it. Thank you for articulating the importance and really one of the greatest feats of human achievement in semiconductors and how we're going to have to navigate the next few years. Welcome me in thanking Chris Miller and Chipboard.
Thank you. Thank you.
That was great. I really appreciate it.
Thank you for joining us as we seek out insights that help us better understand our rapidly changing world. In our next episode, Karina Funk, co-portfolio manager of our large cap sustainable growth strategy and chair of sustainable investing, will speak with Kim Budell, director of the Lawrence Livermore National Laboratory. Dr. Budell's job is to develop and apply the world's most advanced technology to make us all safer. Along the way, her team recently achieved a remarkable breakthrough in nuclear fusion. We hope you'll tune in. Until then, be well and stay safe.